Recording in progress.
All right, good evening, everybody. Hopefully, the internet, I guess, people are with us tonight. But if I do lose you, and who knows who becomes the professor, just bear with me. Give me a few minutes, and I should be able to get back in. But maybe this won't. Maybe this won't happen tonight. So today we're going to be doing the notes for this unit are a little bit different, just because I want short timing of how long things will take, and a lot of it is combined. You'll see these notes are for 4-4, 4-5, and 4-6, and we're going to just do these whole week. So I'm hoping, to get through maybe half of this today, and then pick it up on Thursday. And so I kind of made it all one, and then you'll see, like, if you look, on Blackboard, there's the 4-4, 5-6. This is going to be first. And then there's the 7-1-4 and 2-3. Like, so again, it's kind of different sections are combined. So this is the reason for this. And then 8-4 and 8-5. And I just didn't separate it. And you already see, you should already see this section, Jakob. I'm just saying that they're combined instead of like 4-4 is its own, and then 4-5 and then 4-6. So I just wanted to let you know. Okay, so we'll get started. Yeah. So hopefully everybody's doing well. And today we're covering 4-4 and 4-5, or the start of it, possibly finishing it, which is just more rhythms on fun. Lit less exactly. So if you didn't like the trig, we're now on to logs and maybe bigger or better things, or not, right? So looking at this, we've seen logs before, right? Or, well, hopefully you remember. And we're going to talk first about bases of logarithms. So log, the regular common, it's called the common log. This is in your calculator. And, well, okay, David's saying no more trig. I'm not promising no more trig, period. I genuinely don't remember. It has been a long day for me. I maybe got 2 hours of sleep. So we are just, we will see how this goes, right? But everything is good now. We are all here and, doing well. So yeah, maybe no more trig. David, if you're upset about this, maybe I'll throw in some trig just for you, right? Little extra trig. But so the common log is a base of 10. So we never write like log base 10, because the base 10 it's the common log. It's what's in your calculator. That's what's known. Then we have this log base. Normally I write B, but log subscript A here of X. And this is a base A. This is not a common log. This is just any other general log. Maybe that's what I would write in here, like a general log. And then we have my personal favorite, for whatever reason, I'm not totally sure, but I always say it's because you write the least amount, but maybe that's not true. So ln of X, this is base E. So it's the same thing as if I was to write log EX. I mean, why would we write this, right? Well, we wouldn't. So natural log is log base E, right? And to evaluate these, so there's different ways that you could do this. For these ones, it looks like we don't need calculators for, okay, yes, there's a way to do this on a calculator, but you do not need calculators for these. And you want to find the exact answer and evaluate. So these are all like log form, right? This guy, and that guy. But what I would do if you struggle with logarithms, if you understand it and you're like, oh, you look at this and you know the answer right away, awesome. But if you don't, I think of what's exponential form. So exponential form is like, if I'm thinking of the general log, because that's going to be the easiest here, it's base to the exponent equals, my answer is how I always say it. So, and if I I mean, I'm using log base A of X to say this is the same thing. Like if I say this equals answer, oh, maybe that's not a good way to phrase it. But if I said this equals, Y or something, then I would be saying Y equals A to the X. That's how we rewrite it in exponential form. And maybe a better way for me to say this is log base goes here. What I call the answer goes here equals the exponent. And then base to the exponent equals the answer. This is kind of how I think of these two equations, as they're the same thing, right? Written differently, right? So if you can solve it better with the log, then you write it that way. If you can solve it better with base to the exponent equals answer, then you'd write it this way, right? So for example, this first one, I mean, it says to evaluate. So like I would think in my head, this equals what? Question mark. And 2 is my base. So I know I have 2.
Already? Dang, that didn't take long. Oh, there we go. Should have gotten Spectrum.
Okay, can the class hear me? Can you hear me?
Yes.
Okay, so I'm on the iPad somehow, but I'm not on my laptop. So this is creepy. And I mean, I'm getting back on the laptop, and maybe I just joined on the iPad because I don't lose it on the iPad. And it just means you guys won't be able to see me, but yeah. Okay. Well, here we go. So, okay, let me fix this, but I don't know. All right, give me a moment. Sorry, guys. You didn't hear my freak out since my audio was.
Somebody said it's not even 6:30 yet, which is when it usually happens.
Yeah, right. So
maybe you can join individually from your laptop and iPad.
yeah, I do join individually. That's how I do it. They're not connected. So so this is where we're at right now.
Maybe you can use your phone as like a Wi-Fi hotspot and don't even use your wireless.
This is true. Yeah, clearly my personal computer just hates me. I don't know. But okay, let's continue trying. If I lose it again, we'll stay on maybe I'll just stay on the iPad. I didn't realize my iPad was still on, so that's why I was like freaking out. And then I'm like, oh wait, so I'm still sharing my screen. Everything's fine. Okay. So I could have just kept writing, but nobody would have heard me. Okay. If you don't like what I was saying was if you don't like the question mark, then just write, X or what, well, okay, don't write X maybe, but like write Y or something, some variable, right? That's fine. But 4 to what power is 1/16. Now I see a fraction and I know that means the power just has to be negative. So I really am thinking in my head, right? I'm really thinking, okay, these are my like thought bubbles. 4 to what power equals 16, and then I just make it negative. So this means it's going to equal -2, right? And maybe, I didn't write this in the right. Now, this next one's a bit weird because I have natural log of e to the fifth, and I know the base is e. So if I'm thinking about what this is like saying, remember, this is e. So e to the question mark equals e to the fifth. Well, I almost feel like I've cheated here, but this is just 5 if I evaluate this, right? Because natural log of e to the fifth, there's a rule, which I don't know. Oh, we're going to look at it below, I think, or maybe we'll get there. But there is like a property that says if you have your base and then you have a base with an exponent and these bases match, your answer is just whatever the exponent is, right? And you can also just solve that. Now this one, I'm going to rewrite it because square root, we don't know what that means really, but I mean, we do, but this is like 10 to the 1/2. And again, remember, this is a base 10. I don't ever write this, but it's a base 10. So this just means my answer is 1/2. My answer is the exponent. Now this one, again,
Oh my god.
-5
Dang.
because I have the same base. And so my answer is just my exponent, right? Yeah. All you got to do is rewrite it. This is nice. They look complicated, but it's like, oh, the answer is right in front of your face, right? So in this last one, same thing. Cube root is just a 1/3 exponent. So this is ln e to the 1/3. And again, I mean, I could think about this too much, or I could rewrite it like I did here as e to the question mark equals e to the 1/3, but I just know it's going to equal 1/3. And now here's again, something that hopefully.
Sorry, I couldn't.
Oh, yeah.
Your voice is gone, so I couldn't see what did you do for E and F.
Oh, sorry. I don't have chat up.
Yeah, you kind of froze for a second.
Oh, of course I did. Okay. Okay, so sorry, I did not pull the chat up. So re-explain part F. Is that what we want?
E and F.
E and F. Okay. So for E, I rewrite this. I just rewrite this as a to the fifth, right? And then because I have the same base, a here and a here, that like if I just say, oh, a to the question mark equals a to the -5, well, I know my answer is going to be -5, right? So this whole, expression just -5. And then F, I did the same thing. The cube root, this right here, is the same thing as this right here. Cube root of E is e to the 1/3. And because I have the same base, this is like saying e to my answer equals cube root of E or e to the 1/3. Yes, ln and e cancel, and then like log and 10 will cancel each other, right? Or log a and a, like if you have the same, if it was a 2 and a 2 or a 5 and a 5 or whatever, right? If the log base and not the exponent, if the log base right here and then the base of the whatever's right here, if those are the same, then they cancel each other. Yeah, yep. And now we have these summary of some properties. So the first property we'll call the product property. And that's where if I have log base b of x plus log base b of y, so I'm adding 2 different log statements, then it equals the same thing, 1 log statement where they're multiplied together. And then the second property is the quotient property, right? And it's where we have minus log b of x minus log b of y is log base b of x divided by y. So notice like plus goes with multiply and minus goes with divide, right? And then our last property is if I have log base b of something like m to the p, I can actually take this exponent, like if these are different, right, we can't solve, and I can take this exponent and move it to the front. So I get p times log base b of m, and these are the same thing. And these properties are really nice for when we want to simplify or solve or expand or something like this, right? And it's very similar, if you think about it, to multiplying, like if we wrote this in exponential form, if I wrote a to the m times a to the n, or maybe I'll do b because we used b here. So like if I had b to the m times b to the n, this is the same thing as b to the m plus n. So multiplication goes with addition, right? B to the m over b to the n. This is the same thing as b to the m minus n, right? And then if I have b to the m all raised to the n power, it's the same thing as b to the m n. So these are very similar. I mean, not exactly the same, right? But these are the properties of exponential functions. And they have similar qualities. Oh, good. Now you understand and remember. That's great. Okay, excuse me. So number 2 is asking to write the logarithm expression as a single logarithm with a coefficient of 1 and simplify as much as possible. Okay, so what this means is they're going to give us something, like in this case, we have 2 ln's. We want our answer to just have 1. Or in this case, we have in part B, we have 3 ln's. We just want to combine it to make 1. So we use these properties to combine them, right? So I see this minus here. I know that I'm going to use the quotient property and end up, right? So let's give this a try. So this is going to be ln of what's first, so 5e squared, divided by ln of 5 square root e. But the exciting thing, and you don't need these parentheses, but maybe it keeps everything together. But the exciting thing is that now, I mean, not only do 5 divided by 5 give me 1, so that's cool. We don't need to write that anymore. But I also have this right here. I'll write it off to the side or maybe further. This is e squared over e to the 1/2. So based on that property right there, I can say this is e to the 2 minus 1/2, and I can reduce that to some other number. It's a fraction, I know, but that's okay. So this is going to actually equal ln. We get rid of the 5 over 5, that's 1. And then we get e to the 2 minus 1/2. So that should be 3/2, right? 2 minus 1/2 is 1.5. And I wouldn't write 1.5. I would write 3/2. And the cool thing there is, okay, we got it down to 1 log, but now in this special case, I know natural log is base e, and I have a base e here. So this actually just reduces to 3/2. And this kind of complicated thing that we started with is just 1.5 or 3/2, right? Now the next one, we will leave it in log form because we have some variables, but that's okay. So what I see first, and you can work from left to right. It's kind of similar, like whenever you'd read like maybe your PEMDAS or, something like that, but we can work from left to right. So I see this minus first. Oh yeah, question?
Yeah. Does it matter which one goes in denominator?
Yes, it does. It does. The one that's subtracted must go in the denominator. If it's added, it must be in the numerator. Now, unless it's, yeah. Oh, are you talking for part A? Oh, yeah. So yes, it does matter. So the one that's subtracted is this one. And so that has to go in the bottom. Does that make sense?
Okay.
Okay. Yeah. Because the property says, if you look back right at this, at the quotient property, so the one that's subtracted, you'll see like X and Y is in the bottom and Y was subtracted and X is in the top and X was the first term. And maybe that was too dark. I don't know that, but yeah. You'll see like X and then Y, and so it's X over Y. So for this next one, you could do one giant step, or we can break it down. So I will break it down just to hopefully help all of us. And we will see that I'll first start with these two, right? So this is ln x over 2x. Okay, so I'd have ln x over 2x, which we can simplify, but then I still have plus 2 ln y. And actually, maybe I will do a few steps in one here. This 2, I'll bring it in as squared, right? So in this case, we have ln x over 2x plus ln y squared. Now, combine these two and say, okay, and you could simplify first if you really wanted, like the x over x. Okay, we can get rid of x, but I'll keep it and simplify at the end, just so you see. But I get ln, and this all is multiplied together. So I would get xy squared over 2x. And again, my x's will cancel out. So my final answer here is ln y squared over 2, right? And I don't remember what show that's a Jeopardy where you're like, answer. Maybe it's not Jeopardy, but it's one of those, right? Okay, so hopefully that makes some sense. If the x cancel, like if it was x and a w or something, we would just leave them and it would just be all of that mushed into the one ln, right? And that's perfectly fine. Okay. All right, let's try part C. Ooh, all right, now we've got some logs over here. So for this one, again, I see 3 logs and I see a lot going. So what I might do first is I might say, let me do my exponent. Let me put the exponent in here and rewrite it. But I could also combine at the same time. Like, again, this is totally up to you. Oh, actually, there's a few ways you can do this. Okay. So if you want to do the exponent thing first, okay, if we want to do that, then I'm going to rewrite it. We would get log base 5 of x plus 5 to the negative 2, right? Plus log base 5 of x plus log base 5 of x squared minus 25. Okay. But this right here, x plus 5 to the negative 2 is 1 over x plus 5 squared, right? So if combine these, even though these are all pluses, so like everything's going to go and then everything's multiplied together, that is in the denominator, right? Because it's a negative exponent. So we'll do it a second way. This is the first way. So then I would write, so now I'm going to combine all 3. So I'm going to say log base 5 of everything multiplied together. So each piece, and I'm going to call it like piece 1 is this guy, which was this. Piece 2 would be just x, and piece 3 would be this, x squared minus 25. Log base 5 of 1 over x plus 5 all squared times x minus 25. And all of this is like multiplied together. Now, x squared minus 25, it factors, right, to x plus 5, x minus 5. So I think I can cancel some terms here. So I'm going to get log base 5, and then I'll put x in the top, x 5x plus 5. I'm replacing this with this factored form. That's all I did, right? And then I say divided by x plus 5 all squared. This is looking good, but I can cancel. So I have one more, I can cancel one of the x plus 5s, right? So then my final answer here is going to be log base 5 of x times x minus 5 all over x plus 5. Now, I told you there is another way to think of this, and let me show you that. So the other way to think of this is to think of these two pieces like being added together, but then subtracting this third piece. So I'm going to rewrite this problem, same problem, just different order. Ready? So I'm going to say log base 5 of x plus log base 5 of x squared minus 25 minus 2 log base 5 of x plus 5. So now, if we think of it this way, and we only bring the 2, we don't bring the negative, we only bring the 2 here, right? So we bring the 2 in, and then we start to combine. These two become log base 5 of x times x squared minus 25. But then I'm subtracting this guy, right? So that means that this goes in my denominator because I'm subtracting it. So I would then take, let's see, I would take this and divide it by this. So I'll rewrite that. We'll say this equals log base 5 of x times x squared minus 25 over x plus 5 squared. Now, maybe we got here faster doing it this way, rewriting, but maybe I also just was, taking more time on the other way. I don't know. But either way, they're both correct. And they're both, you can think of it however your brain, whichever way your brain goes towards, that's perfectly fine. And then you still would want to simplify, right? Simplify this, and then you'll get this same exact answer. Log base 5 of x times x minus 5 over x plus 5. Yeah. Yep, got it. So initially I took this -2 in the front, and I said, and I used my exponent rules, and I moved it here. So then I got this, right? And when it's a negative exponent, that means it's 1 over whatever you have to that power. So it's 1, so that got this 1 over x plus 5 squared. Yeah. And again, it might be easier to just subtract it at the end. I'm realizing that was a little bit quicker, right? Yeah. Yeah.
Is that an example of simplifying that problem?
Yeah, I would say. And again, similar to the way that remember when you verified in the previous unit, right? And you had to verify using angle, double angle, whatever. There were some ways you did it like it was quick and you figured it out, but there were other ways where you could do it and it takes you 5 more steps, but it's the same, you were using the same thing, right? So this is kind of that, like if you want to compare it to that, I think they're similar.
Thank you.
Yeah. Okay. So 3 expand form. What this means is they give this crazy log in all of this, x plus 1 squared over square root of y times z squared plus 1, like all this stuff. And we need to write it in as many logs expanded as long as possible. Seems safe, but we want to see, do we know our rules or not, right? So if I do this, I always start with the numerator and then the denominator, and then I go from there. So I start with the numerator and I have that's positive, and then you can break it down if necessary. And then I go to the denominator. So numerators first, and maybe I'll keep it in green, log of x plus 1 squared. Okay, we can, if that needs to be expanded more, we can. But now I go to denominator and I know I subtract minus log, and I have this whole thing, square root of y, z squared plus 1. I know I can separate it, but I'm gonna one step at a time, right? So first thing I know is that I can take this 2 and bring it in front. And then that one's all set. That can't be simplified anymore, right? So I'll rewrite that here. 2 log x plus 1. All right, that's all done. But then I have minus, and then I have this monster right here. So I know that square root of y and z squared plus 1, they're being multiplied, right? So these can be separated because they're being multiplied. So I'm going to keep, the tricky thing is this minus here. I'm going to keep them in parentheses for now and separate them, and then we'll make it nicer for our final answer. Okay. So I'm going to say log square root of y plus log z squared plus 1. And again, this is one way to think of it. If you'd rather not have the parentheses, you can think of it, everything in the denominator has to be minus, everything. So see how I have parentheses? So if I distribute this minus, these are both going to end up just being minus. I wanted you to see it's broken apart as plus, but because they're in the denominator, they're minus. So now, and again, you could skip to this step. I can rewrite it again, 2 log x plus 1 minus, now I'm writing extra steps here. You can skip, say minus log of y to the 1/2. I'm changing the square root to 1/2. And then minus log of z squared plus 1. Okay, nothing can happen with that. That's just kind of its own. But I can do one more step, right? I can take this exponent and bring it in front. So my final answer is going to be 2 log of x plus 1 minus 1/2 log of y minus log of z squared plus 1. And this is my extra long drawn out problem that we were condensing before. And now, if you have seen this before, great. If you haven't, it might change your, blow your mind. That's what I'm hoping, right? This is the goal. Change of base formula. So it definitely, it blew my mind the first time I saw it, and maybe you'll see why. Maybe you'll think, yeah, this is fine, whatever. But if I have something, and okay, this says base B, but, okay. They broke it up, base B, base 10, and base E. Okay, so you can do this. Really, we never do it base B. So I don't know why they did that, but they broke it apart. And they said, if you have this problem and it says log ln, doesn't really matter. But if you have log base A of X, you can actually solve this by rewriting it as log base B of X over log base B of A, or log of X over log of A, or ln of X over ln of A. Now, what I have to say about that, and what's kind of crazy, I'll just do maybe like a quickie example. I mean, we're going to see some, but is if I tell you to evaluate, okay, I don't know. Okay, some positive numbers, but give me any 2 positive numbers. Maybe someone give me 1.
3.
3, and then give me another number that's not 3. 6. All right, I said in the chat. Thank you. So, okay. So if I said, what's log base 3 of 6? Okay. I mean, the way we would normally do this is we would say 3 to the question mark equals 6, but if you said 9, I would have been like, oh, that's fine. But 3 squared is not 6. It's 9, right? So we don't know what this question mark is. It's a decimal for sure, but we don't know what it is. Now, if you wanted to find it, you can, I prefer base E, but either of these are better. Base B does not help unless you can solve for it, but I'll explain why. So you can pick either base 10 or base E. Again, I prefer E, but if you like log, you know, that's fine. And you can write ln 6 over ln 3. And if you put that in your calculator, that is the answer. And it could be log 6 and log 3. You just have to be consistent. So the crazy thing is, even though this is complicated and we could never solve this just on our own, if we just use this change of base formula, we get this. And David asked, why do I prefer E? Is there a benefit? So I think again, there is no benefit. Literally, it's the same thing. But I think one, to not write an extra letter, like literally log and ln. I think that's my weird math brain preference. But also in higher level mathematics, a lot of times you use E, like you just use the exponential. You never use base 10. I don't know why, but we always use natural log for everything. So I think I was more accustomed to it, and that's why it's more, yeah, that's a good question. And I should know why. No
So
good reason.
can I just mention that
Yeah.
that on like the TI-84 calculator, for example, there is a way to enter any base.
Yes.
By going
Yes.
to the
So
math
I will
function,
say when I
anyway.
learned this, and you know, I'm not saying I'm ancient or any of us are ancient, but when I was using a calculator learning this, and even the first few years I taught it, that was not a button, right? You could
Right.
not, you actually
Right.
could not put the base as any number.
Mhm.
And maybe as I was teaching, this is when it happened, but at least that I can remember, like this was not a thing. So I'm very used to this is not a thing, right? So this is
Mhm.
probably why they include base B, because on your calculator, but that just means that you could put this on your calculator, you know? And so that
Yeah.
kind of ruins the fun, but it's okay. And
Oh,
for
yeah,
natural log, yeah. And we have a question for natural log. Will the base always be E, or is there any other? No, okay. So the answer to is there any other base is no. And will the base always be E? Yes, it will always be E. Yeah. And like, if you see it on your calculator or, you know, wherever, you know, whether it's on Desmo, I don't know, whether it's online, it will always be base E, and log will always be base 10. Those are, I mean, if those change, I don't know, some ancient Greek mathematician probably did something. I don't know. But yeah, this will not change, right? Okay. So now we want to get these decimal approximations to 3 places. Now this is a bit boring because you can just put log 64 in your calculator. So feel free to, and if you're on Desmos or whatever you're on, if on your phone, you could do this on your phone calculator. But log 64, nothing fancy, just hitting the log button, and then 64, and I should use a better color. And this, I get about 1.806. It says 3 decimals. So just check that you can do this, right? Because this shouldn't be too difficult. We just want to make sure we're all on the same page. Then ln3, this is about 1.099. Now the fun stuff for number 5, use the change of base formula, okay, and a calculator to approximate, to 4 decimal places. So again, okay, if you want to be cool and use your base B, go for it. But and you can pick whatever B you want, right? But I'm a little bit lazy, but also, you know, traditional maybe. And I'm going to use the base E, and you can also use log. So like, for example, I'll write both for this one, but you pick yours and we should get the same answer. So if you like log and you're going to do log 15 over log 7, it should be the same thing as ln 15 over ln 7. You cannot mix log and ln, right? That's where you'll get the wrong answer, because then you're mixing up the bases, and that's not kosher, right? So my approximation here is 1.3917. We go to 4 decimals here. And then this next one, I'm just going to use my handy dandy ln because I just love it. And then ln5, maybe it just looks cooler. Like, I'm not really sure, right? Maybe log looks cool. I don't know. This is a negative exponent, and it's because 0.3 is smaller than the base point. That's 5, right? So this is negative 0.7481. Okay. And what this means, if you're thinking like, okay, who cares? Like what we solved for that, but like what does that even mean? Well, what this tells us is that 7, because look, if I look at this, 7 to the 1.3917, okay, we're not exact here, but this should approximately equal 15, right? And that makes sense because 7 to the first is 7 and 7 squared is 49. And 15 is closer to 7 than 49. So 1.39, that's closer to 1 than it is to 2, but it's in between. So this makes sense. Like it's logical, right? So if you got like 92.6, you'd be like, I pushed the wrong button here because that shouldn't make sense. And same thing with the next one. What this tells us is that 5 to the negative 0.7481 is approximately 0.3. And again, you can put this in your calculator if you don't believe it. Which this also is the same thing as 1 over 5 to the 0.7481. Yeah. Okay. So moving on from that cool formula, but now we've got some other things that we can look at, solving log equations. So now we're going from an expression to an equation, and we're going to solve, right? So we have our equivalence property, simple. Okay, so if I have log base A of X equals log base A of Y. So if I just say log of 5 equals log of X or whatever, then this is only true. This arrow means, it means if and only if, which you could also write this as IFF. And again, math people love to shorten things, make it be lazy, and then say it means something, whether it makes sense or not. And this to me does make sense. Like if and only if, writing that out, that's just like, why would I? So using this double arrow or using IFF, right? Those are also good. But it's if and only if X equals Y, right? If your bases are the same, you're doing log of both sides, then X and Y have to be equal. That is the only way that this first statement is true. Which tells us, this tells us that log is a one-to-one function because it cannot have multiple values for like when we have like X squared equals A, or okay, maybe I shouldn't say A, maybe 100 or something. It could be 10 or negative 10, right? So X here in this case, it's not technically one-to-one. We'd have to restrict that domain because X could be 10 or it could be negative 10. But in this case, we can't have that. So looking at this problem, first problem, they're taking it easy on us here. We have log X equals 2 log of 2 minus X. Okay, so first thing first, I want to get this in my exponent, and then I can set things equal and solve, right? Because I want it to look like log of something equals log of something else. So that's what I'm going to do. And I'm going to say this is the same thing as log X equals log 2 minus X squared. Okay. So now I can say, all right, logs, done with them. And we're just going to solve for a quadratic. So yes, maybe this is more work than I was anticipating, but then we can drop the logs and say X has to equal 2 minus X squared, which we will have to expand this, right? So, okay, this is for those of you that want to like see, what's going on in my head. It's crazy, but this is what we do, right? We multiply all these guys. And I'm just going to write it below. So I get X equals, so 4 minus 2X minus 2X plus X squared. Okay. So this is gross. Like I want to rewrite this nicer because ew, like there's a lot going on, right? But I also want to subtract this X so that one of my sides equals 0, right? So here we go. Let's do it. Cancel this. I have 0 equals. I'm going to write the X squared first because I want to write this in order and then try to and solve. Maybe I'm going to have to do quadratic formula. That's okay. X squared,
I have minus 2x, 2x, and 1x. So minus 5x, that's 2, 2, and 1. It's 4, 5. And then plus 4. Okay. Now, the good news is I think we can factor this, so we do not have to do our quadratic formula. So I'm going to see, I think, because I want two numbers that multiply to 4, but add to -5. So I do 1 and 4, and they both have to be negative, right? Does log need to have the same base to solve? Yes. So great question, Jakob. Like if this was log base 2 and this wasn't, we would have to rewrite this problem. It would not be solvable like this. Okay. So good question. But luckily you won't really encounter that. Or if you do, you can say, you know, I can't solve this because they're different bases. Or maybe later we'll have a solution for this, right? Now, what I want to note, okay, so I'm not done, I didn't finish, right? So here I factored, so I get x minus 1 equals 0, or x minus 4 equals 0, so x equals 1, or x equals 4. Okay, good stuff. So let's just check. So the only extra piece of logs is that usually, so I'll make a note up here, logs usually have what we call extraneous solutions. I don't know if you remember this from before, or because it's happened before. I don't know if it was with trig, but it also happens whenever we get imaginary solutions. Those are kind of known as extraneous, or just, well, they're not real, but like sometimes when you're solving something, if you plug it back in, you need to, the trick with logs is that we solved all of this, but because we did ignore the logs here and we solved just the inside pieces, we do have to double check at the end, do both of these numbers work? Because a lot of the time, and I mean like 98% of the time, they're extraneous solution, right? And so the way we check is we say, okay, here's my two answers. So say x equals 4, well, I just switched the order, but x equals 4 and x equals 1. So test them. So I'm gonna write, this is our check. So we take our original log equation. Well, yeah, I mean, you can take the original or the one we kind of rewrote, and we can just see if this is true. So let's check the first one. Log 4 equals 2 log 2 minus 4. Now you'll see what happens here is this side becomes 2 log, we want 2 squared to get 4, but this is -2, right? And even though we could square it and it becomes 4, the point is on it so that we don't have to square it. The 2 is in front. And we want it so that we could solve just for this piece right here, but this is out of the domain. So if you put this in your calculator, log -2, it would say error, right? Because it's outside of the domain. So out of the domain of log. So this is extraneous. So we go like this, and this is extraneous, right? But let's check 1. I mean, hopefully 1 works, because otherwise then we don't have any answers. So we have 1 is going to equal 2 log of 2 minus 1. And now I'm feeling like I did something wrong, but this, so even though, I mean, these don't look the same, right? 2 log 1, even though these don't look the same, this is in domain. And that's actually all we care about. So we will say x equals 1 is going to be a solution. Okay. So this one's good. This one was bad.
Ten to the 0 is equal to 1. So both
Oh,
of
and
them-
there we go. That's why. Yeah. So if you
they
multiply
are
that by
equal.
2, doesn't matter. Right.
Yeah.
In the domain, yes. And so Veronica asked, in the domain because it's positive, in the domain since it is greater than 0. It just has to be bigger than 0. So whenever we have log of, log of something, we cannot put this in our calculator if it's negative, or we cannot solve if it's negative, because what that tells us is that some number to a power, like square it, cube it, square root it, it equals a negative number. And that's not possible for exponents, right? Okay. All right, cool. So that was involved a bit of work, but we're happy with it. Now here's what they're calling maybe less simple property, but the equations with non-logarithmic terms. So this is what I was referring to earlier in class. Log base b of x equals k. If that's your equation, and I think I just said equals y, but if it equals k, I think I do like that better. And we have in this this if, right? So this means if and only if, and then we have x equals b to the k. And we have log form, exponential form, just like I described above. And the way that I wrote it, so I'll label this, but this is our base. This is our answer, and this is our exponent. And then when you look over here, it makes sense. This is our exponent. This is our base. And this was our answer. Right? So it makes sense. Now to solve 7 and 8, to solve problems like these, we are going to do a little bit of rewriting. And then we're gonna maybe some property first and rewrite in exponential form and solve, just kind of the way we did before, but there's a little bit more involved, right? So looking at this first one, number 7, 2 log base 3 of x equals -2. Well, before I write this in exponential form, I want to bring that 2 into x squared, right? So I'm going to have log base 3 of x squared equals -2. Now I'm cooking. Now I can say, okay, rewrite, because I can only write if it's in the single log form. Like otherwise maybe it works, but it's not going to make some sense if you get rid of the log. So now I can write it in exponential form and say 3 to the -2 is going to equal x squared. And it's like, okay, well, this means that x squared, this means that, let's see, 3 2 is 1/3 squared. That means that's x squared. And the cool thing about this is, well, you could write this as 1/9 and square root both sides, right? So, and say plus or minus the square root plus or minus, oh, I guess I don't need to write plus or minus on the other side, but I could say square root plus or minus the square root, or I just know that this 1/3 squared, this is the same thing as 1/3 squared, and it's equal to x squared. So granted, I don't get my plus and minus here, so maybe you do want to take the square root of both sides, but I would get that x is going to be plus or minus 1/3, but don't forget, it actually might be better to do it the way, this second way that it right here, because you have to check for extraneous solutions again. So we have to check. We get that maybe this is the answer, but we have to check that, is this true, right? So if I check 1/3 and -1/3, and I went too far before, I don't have to solve it. I just want to see, is it in the domain or not? So look at the original right here and just say, okay, I'm doing log base 3 of x. Is 1/3 in the domain? Check, in the domain, good to go. Is -1/3 in the domain? Absolutely not, not in the domain, not good to go. So our only answer, so I would say our only answer is x equals 1/3. And again, the nice thing is, if you solve it that second way, even though you might want to say like, oh, I should probably check for that. And it's probably more important to check, like always get every possible answer and then check it. But if for some reason you kind of just stumbled upon it and then got just 1/3 and didn't even think about the other one, I think like the first time I've ever taught pre-calc, I want to say I had to like take points off for that. Like we wanted you to get every possible answer, but unless I'm asking for it, I don't think it'll necessarily matter, right? But okay, but we want to get all the answers. So let's see what's going on in the next one. So now I have log base 2. They're both log base 2. That's good, but they're added. So I can't write an exponential form yet. I have to combine them. So I use my handy dandy product rule or property, and I write log base 2 of x times x minus 2 is equal to 3.
May I ask a question on number
yeah.
7? I'm sorry.
Go ahead.
Could you have solved it as well by just, can you divide both sides by 2 as the first step? Or
Yes.
would you
So
use
yes.
the power property?
Yeah, you can definitely do that. And that's another thing. Like I was just using the properties, right? But you can definitely divide by 2. You just couldn't rewrite it in exponential form and then divide by 2 because that wouldn't work, right? So that's the point. The point is you either want to divide by 2 or move the 2 into the exponent, because if I wrote this as 3 to the negative 2 equals, or 2 times 3 to the negative 2 equals x, then I'd be dividing by 2. It's not going to work, right? So,
right.
and maybe there by some miracle it would, but typically it's not. So you'll want to either divide by that 2 first or move it in with your exponent rule.
Move it over. Okay.
Yeah.
Thanks.
Yeah. Okay, so this next one, so now we have log base 2 of x times x minus 2 equals 3. So, okay, I can rewrite this now in exponential form because I've got one nice log. So my base is 2, my exponent is 3, and it equals this whole x minus 2, okay? So I'll rewrite that again. So I'll get 8 equals x squared minus 2x. And then I'll subtract 8 from both sides. I'll rewrite it as 0 equals x squared minus 2x minus 8. And then I can factor, and it's really nice, right? So I get, let's see, it's gonna be 4 times 2, but I want plus 2, right? Yeah. So again, I'm getting these 2 answers, but remember the domain thing. So I get x is negative 2 and x is 4, but look back at what I have here. I have log base 2 of x and x minus 2. If I plug in negative 2, this is out of the domain. And so this one is my answer, right? Because this one is good. Now there are other ways to even solve these problems, but I think they're like more complicated and then they involve some more properties of logs. But if you come across it, like this is true. So if you're reading the book or looking at another example, or you like see a similar problem on a homework and see it done in a different way, but it gives you the same thing, and it uses these properties of logs, then yes, this is not the only way to solve. And just like Michael said for number 7, couldn't you just divide by 2 to start and then go from there? This is correct, right? So there are multiple ways, and maybe not every problem has many ways to solve, but a lot of these problems have different ways because all the properties tie together. And as long as you're using it correctly and like performing the math operations correctly, it's not a problem, right? So yeah.
If you get two positive answers, are they both automatically going to work, or do you then have to still plug them in?
So that's a really good question. And the answer is no, they're not automatically going to work. And it's the case of like this number, when we got, 1 and 4, right off the bat, I'd think, oh, good to go. They're both positive, but it was oh dear. Oh, sorry. It was 2 minus X, right? And so if I subtract 4, 2 minus 4 gets me a negative number. And so where you don't, and I did a lot of extra work, like checking this over here. You don't need to do all that. You really would just need to look at this and say, is 2 minus 1 in the domain? Yes. Is 2 minus 4 in the domain? No. And that's how you would figure that out.
Okay. Thank you.
It's a good question. Because initially, when I first learned this, I 100% thought all positive answers were right. So don't you worry if you were thinking that as well, because I was in the same boat. And look at me now, teaching you pre-calc. Okay. So now we're going to go to problem 9. So this one's asking for an exact answer. So yes, the good news is you can still maybe use your calculator, but it's really to check because we want that exact answer. And the calculator might give you the decimal. Oh, just kidding. This asks, never mind. I don't know if your calculator will give you the exact. But let's check out what we mean by this. So my good old ln, right? My favorite. So ln of x plus ln of 2. This combines to be ln of 2x, right? Because we can multiply. And then it equals 5. Okay. So we rewrite this as an exponential. So I say, okay, it's a base. Remember, it's base e. ln is base e. So I get e to the 5th equals 2x. And then I want x by itself. So I'm just going to divide. I'm just solving this like normal algebra. Divide both sides by 2. And I get x equals e to the 5th over 2. So this is my exact answer, right? E to the 5th over 2. Because I don't know what that is, but it's exact. But if you put this in your calculator, then it should be, and make sure you know how to enter e to a number in your calculator. I mean, granted, most of you probably know, but I know sometimes it can be confusing or hard to find the button or whatever. So this would be 74.207. And or 21 if you wanted to round to 2 decimal places instead of 1, 3, whatever I did. I don't know. Or 0.2. Say it just says decimal approximation. So I would accept many correct answers here. And just for, I'm not sure why, but maybe to help with homework or something, but another example that is similar sort of to this would be if I had something like ln of x over 5 equals 3, then I would say, oh, this is the same thing as e to the 3rd equals x over 5. And then I would multiply both sides by 5. And I would get 5 e to the 3rd equals x. And then you could also get a decimal, right? I think the point here was just to show you, the reason I'm mentioning this is to show you an example with a division like x over 5 versus 2x. And keep in mind that this could have started as ln x, let me write this nicer, ln x minus ln 5, right? And well, maybe so it could have started like that and you had to write it as the division and then solve. And now we are moving along to some applications of log equations. Okay, so this says the following formula relates energy in joules, which I think typically it's capital J. I don't know if that's joules or I think it's joules. Raised by an earthquake of magnitude M. Luckily, we're not experiencing that. However, it has been really cold here last few days, hasn't it? Did you notice, right? Did you step outside? Gonna heat up for the weekend, but cold for, they're giving us a little hint of, they're saying, oh, here was fall and then goodbye. But hey, I don't complain. I like this. I like that. Okay, so we have this energy equation. Log E, this energy, is 5.24 plus 1.44 m, where m is the magnitude. So it's saying, what is the energy? And it says A, this is just the only problem. There's no B. I I don't know what happened, or maybe we lost the B, I'm not sure. But what is the energy released by a magnitude 7 earthquake? So 7 sounds really bad. I don't know exactly the, oh, someone said it can be 5 halves. Was that for the previous problem? Probably. Was
Yeah.
it? So it cannot, this answer is not the same as e to the 5 halves.
Uh,
This is the same as 1/2 e to the 5th, like times e to the 5th. But it is not the same. This 2, because we don't have logs, it can't go up into the exponent.
and we cannot simplify with the
Yeah.
logarithm.
Well, and that's why, yeah, whenever you have e in your answer, there's no more simplifying. Yeah.
Okay.
Yeah. I'm glad I saw your comment. There we go. I'm paying attention a little bit. So now our magnitude 7 earthquake. Okay, let's see. And then they give us this little note at the bottom, but we'll see what that means. So magnitude 7. So this is saying like M is going to equal, and we want to find, so we'll say log E equals 5.24 plus 1.44 times 7. Okay, so let's calculate. 5.24 plus 1.44 times 7, I'm getting, look at him, that little handy dandy calculator, like 15.32 maybe, and then log of E. Yeah, right. So that sounds good. And then I have this log of E. So for those of you that didn't like the ln that we all just used, we're back to log. So this is base 10. So we can rewrite this, because just by looking at this, I don't know what it is. I don't know what the n. But remember that this is base 10. So we can rewrite this as 10 to the 15.32 is our E, our energy in joules, right? Now, you can actually put this in your calculator, 10 to the 15.32, and it is approximately 2.089 times 10 to the 15 joules. And I'm just going to write a capital J, again, maybe because I'm lazy, but you could write out JOULES as well. But this is how much energy a magnitude 7 earthquake, based on this equation, right? That's how much energy is released. And they're just noting for us just to get a reference, because I don't know if it sounds like a lot, but I don't know if that's a lot or not, right? And a magnitude 7 to me sounds really bad, but I don't really know. But the eruption of Mount Krakatoa in 1883, so it produced an energy release of 2.09 times 10 to the 19 joules. So this, I mean, granted, yeah, I don't know history so well, but so this, if you know anything about this or you want to Google this, how bad was this? Well, that's how much energy was released there. So a magnitude 7 earthquake is pretty significantly less energy, but not so far, like 10 to the 15th versus 10 to the 19th, right? So add 4 more zeros.
You could put 2.09 times 10 to the 19th on the left, and then get M to figure out what the magnitude
well,
is.
exactly. And you could get M to see, and it should be a little bit higher, I would
Like
guess.
9 or 10 or
yeah,
something.
it should be like 9 or 10, exactly. And again, I at one point in my life, I knew the scale because I looked it up, when there was an earthquake going on somewhere, but I do not remember the scale off the top of my
Well,
head.
it used to be the Richter scale, but then they changed it to magnitude.
Yeah, so it's not, so now,
It's like whatever that
there's
is.
no logic to it. Nothing. And Verona's saying 7, good size earthquake. I mean, it sounds like it, right? To me, it sounds like a 7 is pretty bad. But this formula also, what they say, M has to be bigger than 5. So what that tells me is, if the magnitude is less than 5, maybe the energy is not so significant, or they have a different formula, something like this, right? Okay. So Michelle is telling us that this one completely destroyed the island. So this is definitely worse than a 7, but still a 7 seems pretty bad. And Jakob says it's bad if you're in a high building. Well, good thing I live in 1 story now. No, I don't, or I'm not in the city, but yeah, I mean, I luckily, you know, we are not, or fortunately, we are not going through this, and we did not go through all the Florida disaster that they did, but yeah.
There was this really cool Nova, I think it was a Nova episode where they were talking about the Forbidden City, and I think it's in China. It's really old. It's the way that it's built, it can sustain an earthquake that's stronger than anything that we've ever measured.
Wow.
And it's
That's a place you got to add to your bucket list to visit, right?
Yeah.
That's pretty, I mean, that's pretty neat. Yeah. Very interesting.
Pretty cool.
I wonder how you managed to secure that, you know?
Oh,
Like,
I don't know, but
always
they
looking-
did this test where they created like a simulated earthquake, and they cranked it up, to be
Yeah, that's
powerful,
crazy.
and they still couldn't get this thing to go down. It was
Wow.
cool.
All right. So if you want to be real secure, or you're worried
Yeah,
about that,
move
want to
to the
see if
Forbidden
earthquakes
City.
are hitting us everywhere, go there.
And it
Right.
always came in the night. Like I never.
Oh, while you're
in the
sleeping, so then you
morning.
don't even, so you barely probably have time to
Usually-
even run.
Wake up.
Yeah. Yeah, that's crazy. Well, and I know,
Right.
I mean, my parents used to experience, they were in California for a bit, and I know they would experience earthquakes pretty often, but they were usually very minor, right? I'm sure I could ask them if there was any, but like they always said, like, if one of them was driving, you wouldn't, you don't feel it as if it's a little earthquake, small magnitude. You don't really feel it when you're driving, but but they've said, if they're in the house or apartment and all of a sudden everything will just be shaking and you don't know, like, something wrong with the building, or, and then it will just stop. Like, it'll just happen very quickly. And I think it was really common there. I mean, I'm sure it still is now, but they're not there anymore. So I don't hear the stories. Right. But anyway, all right. Well, interesting formula there for that problem. Now, the last thing we'll discuss, and I think this is getting into like 4.5 and then 4.6, and we might even start the next section a little bit and save, because I think it's a little bit longer, but inverse functions. So inverse, we know what this means, right? We know that an inverse function, if I have, y equals 5x, the inverse, we would have x equals 5y, and we would solve for y, right? This is typically how we would do this. And Jakob's saying arc log. So this is not like, the trig. So for whoever it was that was like, no more trig, yay, this is better. But if you miss the trig, don't you worry, there's still something for you to do here. So this function, f of x equals ln x minus 5 plus 3. And we know logs are 1-to-1, right? Because of the domain. So it has an inverse, it works. But what we're going to do is this exact process that I was just explaining, this simple process of switching, like, why do I keep doing this? Okay, switch x and y. Then instead of solve, I mean, it's still solving, but then we rewrite and we use the exponential form and change it from a log, or we use log form, but rewrite it. I don't know. We'll see, right? In this case, my formula, can replace f of x with y equals ln x minus 5 plus 3. And then I say, okay, if I switch x and y, so I get x equals ln y minus 5 plus 3. Then I want to solve. So solve for y to get the inverse, right? And I would start by subtracting 3 from both sides. So I get x minus 3 equals ln y minus 5. Now, once I have this, I cannot do anything. I have a log. I mean, I can only rewrite it in exponential. So this here becomes the exponent. We know that the base is e, and then we have this is our answer, right? So let's rewrite this. I would have e to the x minus 3 equals y minus 5. Or maybe I should have written y minus 5 first, but that's okay. Maybe I'll swap it. So then I would add 5 to both sides. And I'll rate my y on the left. I would get y equals e to the x minus 3 plus 5. This plus 5 cannot go in the exponent, okay? It has to be separate. And what we do then is we replace this y, like it's not the same as this y that we started with. So what we do is we replace this with f inverse. So we really started with f of x, we wrote y, we switched them, and then we solved for y again, but now final answer is going to be f inverse is e to the x minus 3 plus 5. And the inverse of this original equation is that. Oh, and David's saying the hardest log problem is greater than the easiest trig equation. All right, well, I'm, jury's out, jury's out. And I do think we're going to try to get to at least the first 2 examples of the next section of notes. Well, 1, because my internet's working and we have some time, and 2, because I just know that the notes for the next section are a little bit lengthy. So, I mean, I'm not positive, but I just know it should take us like the whole time. And I don't want to run out of time on a Thursday and then be like scrambling the next week. So let's stick to it. If it's too much and we have 30 minutes left over in the next class, then I can answer questions, or we can, hold I can go over these notes again, anything like that. But I just want to keep it rolling while we can. So, and again, this is like 4-4 into 4-5 and then 4-5 into 4-6. So it's all kind of just mushed together, but let's check it out. So we're happy about logs now. Inverse functions, we saw how to do that. Only ln, but it's the same thing with log, right? So now we're looking at these exponential equations and models. Start with the equations, right? So with exponential equations, spoiler alert, we're going to use logs to solve, and logs are now our best friend, right? Kind of like trig is our best friend, but there's no good SOHCAHTOA song for logs. So maybe we'll research this, or I'll just play the SOHCAHTOA one again, right? Because all of us love that so much. Or just you can get for your family, for your friends, just to, make everyone in a better mood. But okay, so let's solve this. Give an exact answer, it says, and a decimal approximation. Oh, and it's telling us to 3 places. Okay, I should read the directions because sometimes I don't. So I see 5 to the x minus 1 equals 6 to the 2x. Now, 5 and 6 are not the same base. If they were, we could just set the exponents equal and, boom, we don't have to know anything else, but they are not. So what I'm going to do is I'm going to take ln or log of both sides. And again, cue the brain just growing and exploding, right? Because we can take ln or log of both sides. Again, I'm an ln fan, so I'm going to do that. I want to do log, you write log every time I write ln, and we'll see if we get the same thing. So I'm going to do this to both sides, and I want to use a different color. Let's do this. So I'm going to have ln of 5 to the x minus 1 equals ln of 6 to the 2x, right? Oh, and Jakob found the song. Okay, all right, at the end of class, I will take that and watch it. Okay, so I take ln of both sides, and then I use my amazing properties, right? And I take these exponents and I bring them in the front So, oops, what did I do? That's not what I meant to do. Here we go. And I bring them in the front and I say, I have x minus 1 ln 5, and okay, you don't need those parentheses, equals 2x ln 6, right? And now we got something good going, because I can say, okay, I can basically get rid of all the parentheses, get a bunch of terms, and then try to get all the x's together and all the other stuff. And it's hard to tell like what's the other stuff, right? Because like I see ln and it's confusing. Now you could, well, we don't want to divide, so we're not going to do that. I was going to say we could divide, but that is not as nice. So I'm going to distribute first the ln 5 to both of these. So I'm going to get x ln 5 minus ln 5 equals 2x ln 6. And what I mean by get all the x's together and all the other stuff is I want everything with an x on one side so I can take the x out. And then I want all the number stuff and log stuff on the other side. So now I'm going to subtract 2x ln 6, subtract 2x ln 6, and add ln 5. Again, I'm moving, so what I'm doing here is, oh, and you can't really see this yellow, can you? Is move all x to one side, number to the other side, right? That's what I'm doing there. And when I simplify it, I'm left with x ln 5, oh, not plus, minus, right? Minus 2x ln 6 equals ln 5. Now I take my x out and I say, okay, these both have, I see an x here and here. So now I can factor an x and I'm left with ln 5 minus 2 ln 6. Okay, don't know what that is, but that's okay. And that equals ln 5, right? So for my last step, I can divide both sides by this whole nasty thing, ln 5 minus 2 ln 6. I can divide both sides to cancel here. And then look what I'm left with, x by itself, right? So now I'm left with, I'll do this over here, x equals ln 5 over ln 5 minus 2 ln 6, right? And don't try to get fancy, right? We do not need to get fancy here and try to like, oh, but this is like, ln 5 over 6 squared. Like, you don't have to do that. The exact answer is just what you got. So the exact is this, ln 5 over, because you can't simplify a natural log over a natural log. It just, you would have to put it in your calculator. So we might as well just keep it all like this. So there's my exact answer, right? And if we enter this in the calculator, remember to be careful. You want to put like parentheses around the whole denominator, or just, make sure your calculator has done this right. And this should be about, it's into 3 places, get negative 0.0 or 0.815. And again, if you were like, ew, I don't like ln, and you thought I want to use log, then what you would do is every time I put ln, you would just have log in your answer, and it would also be correct. Everybody's got preference, not judging. We all got our preference. Now, for number 2, I will say, although people have preferences, it will benefit you a lot to use natural log just because we have some e's there. And it'll just simplify it a little bit, but you don't need to, still don't need to, still not going to be wrong if you use logs. So let's look at number 2. We want to solve for t. Now, the crazy thing is this right here, equation equals 0, we're about to do something weird. So you think of think of e to the t like, so, okay, I'm gonna write this like off to the side over here, right? So this is for number 2. We think of e to the t as x, right? If we think of it like this, and this is just, if we do this, I'm just trying to connect these dots here. I get e to the 2t x squared, because it's e to the t and then squared, so x squared, minus 4e to the t, so 4x, minus 5 equals 0. If you saw that, you'd be like, I've got this. I can solve. I'm so smart, right? And we just factor this, x minus, what is it? Oh dear. Mine plus 1 minus 5. Oh man, I struggled there, but hopefully you got it, right? And I'd say, okay, my answers are -1 and 5. And I just crushed it. Good to go. Now, trick for you, we can also do this with e to the t. We can literally replace x with e to the t. So all of these x's are e to t's, and then we solve for t by using our natural log. So let me write this out now in the problem, right? So if I think e to the t squared minus 4e to the t minus 5 equals 0, I just rewrote my equation, right? Then I say, okay, I'm just writing what I did here, right? I can say, all right, this is the same thing as e to the t plus 1 times e to the t minus 5 equals 0. I just factored it. It's kind of cool. And then I can do the same thing. So I get e to the t plus 1 equals 0 and e to the t minus 5 equals 0. And then I just solve. E to the t equals -1, e to the t equals 5. Now to get t, we would take log of both sides or natural log, right? I'm going to use natural log, but in this case with e, you probably want to. However, before I even do that, what I'll notice is this guy is going to be extraneous because what do we see? What's going on? This is out of the range of e to the t, right? So if you think of the function e to the t, it looks, I think, or y equals e to the x. It looks something like this. If you were to graph it, and you could just graph this in decimals. Okay, that's, my curve is actually horrible, but okay, that's maybe better, but maybe also just, but you get it, right? So my e to the x is here. My range is 0 to infinity. It's all positive numbers, right? So e to the x or e to the t, it cannot equal -1. That'll be imaginary or who knows, right? So that does not exist. So now we only have to focus on this second one, which is nice. So now we only have to focus on this guy, and I'll say ln e to the t equals ln 5. But remember, ln e to the t, I can take this exponent, bring it in front, and I get t ln e, and ln of e is just 1. So the cool thing here is that this just equals 1. So I get t ln 5. And that was really nice, right? So my exact answer is ln 5. And then my decimal, that in your calculator, and they said to 3 places. So 1 point, so you're just doing ln 5, 1.609. Now, if you did logs here, I want to make an important note. If you used logs, then you would get log e to the t equals log 5. You'd get t log e equals log 5. your answer would be log 5 over log E. It would not just be log 5, right? Because our bases are different. So technically, ln 5 over ln E is ln 5 over 1. And that's why we didn't write it, okay? Because the base of this is E. This is like E to what equals E to the first? Well, it's just 1, right? So when you have log E, you would need to keep that there. You could not get rid of it. So just keep that in mind. Like why I prefer, and maybe this is why in general I prefer ln over log, because this is more often when it cancels and it's really nice. Okay. All right. Okay, so we are going to just get a little bit more into this, dive in, maybe do problems 3 and 4, and then I'll stop. Okay. Yeah, because 5 is just getting into a whole other scene here. But we have seen like a lot of these concepts or applications, we've seen them before, and we're now just applying, you know, our logs to solve. That's all we're doing. So we're not really, you know, we're kind of weaving in all this knowledge that you already have and building it on this new knowledge. And then you just are like a genius. That's basically what's happening, right? And Jakob says, where is Scooby? Yeah, Scooby is a struggle. I mean, he's okay, thank God. But he threw up but from when I went to bed last night till like midnight or 11, he threw up probably like 3 or 4 times, or maybe 5. And so I drove him to the animal hospital, and at literally 11:45 at night, he threw up on the car right there. It's 3 miles away. And we were there till after 1 in the morning, or maybe it was 2 in the morning, and they had to take an x-ray, and they were like, yeah, he didn't eat his dinner. He was like puke, and he ate something. I think he ate something outside, or it might've been I don't know if I told this class, but he ate the bottom of his crate. Who's heard of what dog eats the bottom of their crate? He's got like major issues. So he ate that plastic a week or 2 weeks ago. And the vet said they thought something was in his stomach. They couldn't tell what it was. And it could have been that, because I haven't seen him eat anything else. I brought part. Oh, I don't know what that means, but yeah. So they think, so they had to like flush it out, and they were like, yeah, if this doesn't work, like we'll keep him for 24 hours. But if it doesn't work, like he'll need surgery, whatever. So basically I got home after 2 in the morning and slept for like 2 hours. And then the vet called again at like 5, and then at 6, and then at 7. And then I had to go to work. So today's been a day, right? But Scooby is okay.
Is he home?
Yeah, he's home now. And my husband just took them out, and we just have to basically monitor him. He's a savage. Exactly. Scooby Savage. He suits his name. But he can only eat boiled chicken for the next 3 days. I'm like, what? Like, I've heard of this in concept and theory, but I've never had to do it for anything or anyone, right? So I had to boil chicken. We had to boil chicken tonight, and he can only eat shredded boiled chicken for 3 days. And hopefully he gets better. So, oh yeah, I mean, he would eat boiled chicken for the rest of his life, but I ain't got time for that, right? I mean, I'd put his kibble in a bowl and he'll eat that as well. So, but anyway, so yeah, so Scooby has given us a problem. We love him, but he's the devil at the same time.
On the plus side, he's very quiet today.
Yeah. Well, tonight he's pretty mellow, because he was throwing up for a day straight. So, and he was totally not himself, but yeah, he's getting back to normal. So Thursday, be prepared. He's going to just lose his mind. But anyway, so now, like I was saying, we're taking these old friends, compound interest, and this formula, right? And these 2 formulas, and we're now applying it using logs. So we're going to be solving for a different variable and just use logs to figure this out. So let's check it out. Number 3 says, suppose that a 19-year-old you, oh, wow. All right, we're throwing it back. Or maybe some of you are 19 or were recently 19. But 19 years old you wins $100,000. Dear gosh, wow. We're just pretending our life was better than Scooby's last night. exponentially better, right? If you would like to have $1 million, okay, would love that. When you retire at age 67, I mean, that's more realistic than it used to be like, oh, 55, not true, right? Determine the average rate of return needed for under continuous compounding. Okay, so we are finding R. So we're finding R equals question mark. 19 to 67 tells us that T 67 minus 19, however many years that is, right? And which I think it's 48.
Right.
And you have 100,000 so that you're investing. So this is your P, and you'd like to have the million. So this is your A, right? So this time, this is really different. We're compounded continuously. So we're using, oh, thank gosh, we're using this here, right? So we have A equals PE to the RT. And I know my A is 1 million. My P is 100,000. My E is my E. My R, I have no idea. And 48, and maybe I'll write 48 is my T, if I calculated that correctly. So from here, what we want to do is, oh my gosh, not my T, my AR. What am I saying? Okay. So what we want to do is isolate. We want to isolate this variable, this term with R, and then we want to use logs and solve. And in particular, natural logs, but okay, you can use regular log too, not judging. So first step is we just divide both sides by 100,000 by the P value, right? And really we're just canceling a bunch of zeros. So actually you could use log as well. It'll be nice in this situation specifically, but what we get is we get 10 equals E to the 48R, right? Again, you can use log or ln. I'm still a fan of the ln, so I'm going to do that. So I'm going to say, if I take ln of both sides, ln, then we know, I'm going to rewrite this, and we know that exponent can come in front. So I'm going to say ln 10 equals 48R ln E, right? Now, okay, here's where I did a nice thing. ln E is just 1. So this just goes away because it's just 1, right? And I get ln 10 equals 48R. So now I divide both sides by 48. And when you do this, my only tip to you, and here's my R, is when you do this, ln 10 divided by 48, make sure in your calculator you close that parenthesis, because if you do ln 10 divided by 48, this is going to be wrong. This will be a very different answer. This is not equal to ln 10 then divided by 48, right? So just keep that in mind. I mean, I'm going to get rid of this for space, but keep that in mind. And what I get here is I get that it's about 0.048, who else, who knows? And now this is not my, 0.048 is my answer, but my question was determine the average rate of return. So it's a rate, right? I want to give the percent now. So instead of moving the decimal over 2 times to the left, which is what we normally do, we're going to move that bad boy 2 times to the right. And we're going to say my answer is 4.8%. So if you won the lottery at $100,000 that you could put away in some account, and you retired at 67 and you wanted this to be, what rate you wanted it to be, $1 million. What rate would you need? Well, you need 4.8%, right?
Yeah. Good luck on the rate staying that.
Yeah. I'm like,
staying
there
that
was
way
another,
for that long.
yeah, right. There's another problem I was looking at. Yeah. 48 years. There was another problem I was looking at where earlier, I think for my other class, where it said like you had a 6% interest rate for this account. And I was like, that's more like the mortgage rate. Now, not the interest rate, right? Interest rate's like 1.5, maybe, if you have a good savings account, right?
Right.
Yeah, but, or 2, maybe.
Need to update these numbers a little.
Yeah, right. These are definitely from 2000, some earlier 19, I'm not sure. But yeah. All right, and we'll finish with this number 4 because it's related a little bit to number 3. How much time does it take an investment? So how much time does it take an investment of $1,000 to grow to 8,000? And again, these are highly not realistic for us right now, but maybe if it was a stock, I mean, granted, those fluctuate too much, but if it was a consistent stock, maybe, right? At a rate of 9.5% compounded annually. Okay, so let's figure out what this means. 1,000 is our P, 8,000 would be our A, because that's what we want it to be. Our rate is 0.095, and annually equals 1. So this means I'm using this formula, P1 plus R over N to the NT, right? And what am I looking for? Time. T equals who knows, right? So the first example, we calculated for a rate and we used logs. We can also calculate for the time and use logs. So I'm going to write this out. 1,000 going to equal 1,000 times 1 plus 0.095 over 1. Okay, you don't really need to write the 1 if it's annually, and then to the T. So I'll divide by 1,000 to make this a little nicer. So I'll get 8, and then I'll write 1.095 to the T, right? And now I can do my fancy, and this one doesn't matter if you use logs or ln, they're going to get you the same thing. Nothing simplifies. So if you're that log person, go for it. And I'm going to get ln of both sides. So I get ln 8 equals T ln 1.095. So I divide both sides by 1.095, ln of 1.095.
You don't subtract the 1 from.
Sorry, I added. So okay, this whole thing is raised to the T power. So
I see.
I added that and combined it. Good question though. I did that very quickly and trickily. Yeah. But
Okay.
so this whole thing, yeah, becomes 1.095.
Makes sense.
Yeah.
Thank you.
Yep. And if this was like compounded quarterly or monthly, it'd be a little more confusing because we'd have to, we'd have this extra number that we have to calculate. But this is a nice one because it's annually. So it's easy. Well, easier. And so now our T is just going to be this ln 8 over ln 1.095, or again, use logs. And if we simplify this, if we round this out, I think I got like 22.9, and thinking about what did we just solve for again, because I kind of forget, but we solved for T, so time. So it says how much time does it take? It would be about 22.9, or you could say 23, right? To be a general estimate there. 23 is probably a safe bet, but 22.9 years, that's how long it would take for this situation if you had $1,000 for it to grow to the $8,000. And so next class, we're going to take a look at the exponential growth and decay and the models that you see like here. And what I'll do is I'll post these notes. And even though there's more pages in the next class, I'll just post them again with the added pages that I've written on. So it will kind of be double posted, but that's okay. The question for today, well, based on my night, it's a quick one. And maybe you're neither, but I'm just going to say, I'll give you my answer. So I'm going to ask dog or cat, like, are you a dog or a cat person? And I'm making you decide. But I grew up a cat person my whole life. We had cats and other animals, and I loved cats so much. Now I'm kind of allergic and I still love them. My sister has one, but now I'm totally a dog person, right? Because in my adult person is dog, would say dog, because now I have 2 dogs, right? But yeah, I mean, they're both great. So, Jakob wants me to play the log song. Okay. I mean, I'm not going to, I won't hurt the class by playing it tonight, but we will play it. Maybe next class, since I'll have time. And yeah, a lot of people have both. If you have 3 cats, you have 3 cats, but love dogs.
Yeah, I've never had a dog like as an adult.
Yeah, I mean, and I like, I didn't know what in here, but, oh geez, I'm trying. Oh, it's